Hello everyone. In today's lecture, we're going to cover section 4.6, where we're going to learn how to roughly sketch the graph of a function. In this section, we're going to combine the knowledge that we've gathered in the previous two sections. Remember what we did in section 4.4, we learned how to find the extreme values of a function, and in section 4.5, we learned about the notions of concavity and inflection points, which roughly told us how the graph function curves, whether it curves upwards or downwards. And we learned how to find all this data by drawing a table and figuring out this from the first and second derivative via the first derivative test or the second derivative test. And in this section, we're going to learn how to sketch the graph function using these, but before doing that, I have to cover a couple other notions that are necessary to be able to sketch the graph function. You see, all the other things that we've learned in the past two sections, they're about local behaviors of the graph function. What do I mean by local behaviors? Whether you have a local minimum or local maximum or an inflection point, those things are just about the behavior of a function at a certain region, in some neighborhood of some point, okay? Those things are local data. But sometimes you want to, in order to be able to correctly sketch the graph function, you also need to get a sense of how it globally behaves. What do I mean by globally behaves? You need to understand what happens when x goes to positive infinity or negative infinity, okay? Or if you have some point where you have possible infinite limits, you have to understand the behavior of the function around that point. Maybe at that point your function is undefined, and around it something weird happens, okay? So in this section, before sketching graphs of functions, we're going to learn about the notion of an asymptote. An asymptote is simply a line to which the graph of your function approximates in the long run. Okay, and how can a line look like in plane? It may be, there are like three cases. It may be vertical, it may be horizontal, or it may be a line which is not vertical and not horizontal. And these notions will give you the notions of a vertical asymptote, horizontal asymptote, and oblique asymptote. Okay, so let me write down some definitions for these. So, a definition. The graph y equals f of x of a function f is said to have a vertical asymptote at x equals a if the limit of your function at a from right or left is one of the infinities, okay? And your function is said to have a horizontal, like the graph of your function is said to have a horizontal asymptote y equals L if the limit of your function at positive infinity is L, or well, maybe I should make this a m, okay? Let's make this m. Or the limit of your function at negative infinity is m. And the third type of asymptote is, like, the first case corresponds to vertical lines, the second case corresponds to horizontal lines, and the last case will correspond to gas lines which are not vertical or horizontal. And f is said to have an oblique asymptote y equals mx plus n if this difference f of x minus mx plus n has limits 0 at infinity or negative infinity. Okay, so f of x minus mx plus n, it's infinity, negative infinity is 0. Okay, now let me show you how these asymptotes look like by giving some examples. I mean, okay, we're gonna see actual examples in questions, but at the moment, let me just draw some graphs like this. Let's see. Some arbitrary graphs. Okay, I'm just gonna make up some graphs. I don't know which functions correspond to these. Consider the following function. Let's say that I can do many things at the same time. So let me do that. Okay. Let me take this and delete it. I'm gonna draw a new one. I'm sorry for this. And I think in this big picture I can illustrate everything. Okay, so x, y, let's pretend that this is x equals a, and this is y equals m, and yes, and let's pretend that this is y equals mx plus n. Consider a function which looks like this. Okay, so pretend that this is your function y equals f of x. Okay, I don't know what this function is. I just made up a graph. Okay, but with some effort, you can actually write down a formula defining a function whose graph will look like this. And let's understand what's going on in this picture. So this is the graph of my function, and when I try to understand what this function does at negative infinity, I see that its limit at negative infinity is m. Okay, and this by definition means that I have a horizontal asymptote. Okay, so this is an horizontal asymptote. Asymptote. And when I try to check the limit of this function at infinity, I see that it is infinity. Like it just goes to infinity. But it goes to infinity in a very specific way. Meaning what? As like I tried to draw this in such a way that the graph of this function slowly approximates the graph of y equals mx plus n. What I mean by approximating? What I mean is the difference between these two functions, f of x and mx plus n, the difference goes to 0 as x goes to infinity. Okay? So this difference goes to 0 as x goes to infinity. So I will have, this will be an oblique asymptote, okay? This by definition will be an oblique asymptote. Because when I checked the limit of this difference, I see that it's 0, at least pictorially. And when you check the limit of this function at a from left, you see that it is negative infinity. And this by definition tells you that you have a vertical asymptote. Okay, so this is a vertical asymptote. This is a vertical asymptote. Let me take this and put it over here. Okay, so in this picture, you see all these three types of asymptotes. Okay, now there are a couple of things I'd like to mention. Students tend to think that the graph of a function cannot intersect the asymptote, because what's supposed to happen is whatever your asymptote is, the graph of your function is supposed to get closer and closer to that guy when you take the limit as x goes to infinity or negative infinity, or maybe you're talking about vertical asymptotes and you're taking the limit at a specific point. And students tend to think that like the graph should not intersect the asymptote. This is not the case. As you can see, this graph intersects these asymptotes at many places. At these 4 places, actually 5 places. Okay, you see, I made this like I defined this function at a. I made like this function is defined at a. This is another mistake that students do. Students tend to think that, okay, if I have a vertical asymptote, then at that point my function should be undefined. Well, that's not true. That's simply not true, okay? Like this is still a vertical asymptote and this function is defined here. The only thing you need is, if you want to have a vertical asymptote at a point, a right or left limit at that point should be plus or minus infinity, okay? So 2 points. Vertical asymptote does not mean that your function is undefined there. It may be defined there. And a second point, the graph of your function can intersect the asymptote. And some of you may object to this by saying that, okay, it intersects it, but like, for example, this oblique asymptote, when I take the limit in the limit process, when x is very, very big, it does not intersect. Well, I could have drawn a graph where the graph intersects the asymptote infinitely many times. Okay, I could make these oscillations and I can intersect asymptotes infinitely many times. I can do that. Okay, so don't make these 2 mistakes. And this picture is supposed to illustrate all these 3 types of asymptotes. And let me put it over here. Okay, so I'm now gonna move forward and tell you how you sketch the graph of a function. Sorry, I should first describe how to prepare to sketch the graph of a function. So, question is, how do we sketch the graph of a function? Okay. Here are the steps. Find f prime and f double prime and the intervals of increase decrease and the concavity of the function, the concavity of the function. For this one, you should presumably you'll need to use the first and second derivative tests. The first and second derivative tests. So you're supposed to figure out the intervals of increase and decrease and the concavity of your function. That's the first step. What else should you do? You're supposed to find the asymptotes. If there are any. Okay? And how do you find the asymptotes? You just check these limits. Okay, you check the limit of your function at infinity, you check the limit of your function at negative infinity, and you try to figure out whether those limits exist, or if they don't exist, you try to figure out whether there is a linear function of the form mx plus n such that the difference goes to 0. And besides those, you try to figure out whether there are any points at which the right or left limit is one of the infinities. Okay. You figure out, you find the asymptotes if there are any, and finally plug in some sample points. Okay, for example, you may find the x and y intercepts. Okay, now this data so far, like f prime and f double prime and the asymptotes, they will tell you how your function locally behaves, how your function locally curves, and what it does when x tends to infinity. But these are not sufficient to draw a proper graph, because pretend that you know that your function is decreasing here and increasing here. Okay, decreasing, increasing. Does it look like this or does it look like that? I should compare the values of the function at these points. Maybe they look like this or they look like that. The point is, besides what you learn from these, you should also plug in some sample points to get a sense of well, you should just plug in some sample points. I mean, you may, for example, find the x and y intercepts and so on. Just plug in some sample points so that you'll see that maybe like if maybe there's a local maximum here, maybe there's another local maximum here. Well, there are like two bumps. Which one is higher? In order to figure that out, you should just plug these in, okay? So plug in some sample points. I don't care which ones you plug in. And you can try to find x and y intercepts, for example, if you want. Plug in some sample points, and when you combine, when you do all this, you will roughly get a nice picture for your function. You'll be able to roughly sketch the graph of your function. Now, I'm going to solve 3 examples, and in your recitation you'll solve more examples, so don't worry. And the first one will be the following function: sketch the graph of f(x) equals x minus 2 arctangent x. Okay? And solution. So I need to sketch the graph of this function. What do? I first find f prime and f double prime, and I gather all this data about a concavity, inflection points, and extreme values. So the domain of this function is all real number, the set of real numbers. Like this is defined everywhere. So that's going to be my domain. Let me take the derivative of this function quickly. F prime of x is 1 minus 2 times derivative of arctangent of x is 1 over 1 plus x squared. So I have 1 over 1 plus x squared. Okay, and this is going to give you x minus 1, x plus 1 divided by 1 plus x squared. Okay, so I will have two critical points, 1 and minus 1. Let me also find the second derivative. Let me take the derivative of this term because it's easier. A 0, derivative of 1 is 0, 0 minus 2 times. Now I need to differentiate a 1 over 1 plus x squared. This is like a composition, so I need to use chain rule. The outer function is 1 over t. So what's the derivative of 1 over t? Minus 1 over t squared. So I have minus 1 over 1 plus x squared times I have the derivative of inside, which is 1 plus x squared. So its derivative is 2x. So I get 4x divided by 1 plus x squared squared. So if you set the derivative equal to 0, you'll get x is plus 1 or minus 1. And if you set the second derivative of f to 0, you'll get x equals 0. So I have one candidate for inflection point. Remember, f double prime of x being 0 does not mean that that point is necessarily an inflection point. It's a candidate. Okay? Now I'm gonna do this table. Okay. So I have 3 points of interest. And pretend that this is f prime, f double prime, and f. So I have two critical points here. And I have a point where the second derivative is 0. And now I'm going to fill in this table. If x is less than minus 1, you can see that like the denominator here is positive all the time. And if x is less than minus 1, this is negative, their product is positive. If x is between minus 1 and 1, this is a positive and this is negative, so their product is negative. If x is bigger than 1, everything is positive, so I have this. What about f double prime? This denominator is positive all the time, and at the numerator I have 4x, so if x is less than 0, this is going to be negative. If it's bigger than 0, it's going to be positive. So how does my function behave? Over here my derivative is positive, it's increasing, and it's increasing and it is concave down because I see negative second derivative. And over here my derivative is negative, so it's decreasing and it is still concave down. At 0, the concavity changes, so I have an inflection point. So after this point, I will see a concave up graph. But over here, between 0 and 1, my function is still decreasing, and then it's increasing. So I have, by the first derivative test, I see a local max here, and I have I see a local min here. Okay, and I have an inflection point at 0. So I have completed the first step. I found the intervals of increase and decrease. I found the concavity. Now what do? I check whether there are any asymptotes. Okay. This function is like at every point Okay, I should find a nice way of explaining this. You can find no point at which the right or left limit would be infinity. The reason is this function is continuous everywhere. Its value at every point is a real number, so there can be no vertical asymptotes. So f has no vertical asymptotes. As it is continuous everywhere. It is continuous everywhere. Okay? Because if you're you see, in order for there to be a vertical asymptote, you have to be necessarily discontinuous. Because if there's a vertical asymptote, then at a point, right or left limit is one of the infinities. Well, your function cannot take the value infinity, which means that the limit of that function at that point cannot be its value. So if you're continuous everywhere, necessarily there are no vertical asymptotes. Okay? So there are no vertical asymptotes. If I check the limit of f at infinity, you will get positive infinity, because what's the limit of arctangent of x when x goes to infinity? This is like pi over 2. And this goes to, when x goes to infinity, well, x goes to infinity, which means that you're subtracting pi over 2, 2 times pi over 2. You're subtracting numbers which are tending to pi from numbers which are tending to infinity. You see, this goes to pi over 2. So this term goes to pi, but this term goes to infinity. You're subtracting numbers tending to pi from numbers tending to infinity. Well, the difference will go to infinity, okay? So we have that, and I should also check the limit at negative infinity, and this will be negative infinity as well. So there are no horizontal asymptotes. Okay, I don't have any vertical asymptotes. I don't have any horizontal asymptotes. Now, you should also check whether there are oblique asymptotes. Checking whether there are oblique asymptotes is not as easy as checking vertical or horizontal asymptotes, because it actually requires you to think. Well, these also require you to think, but for oblique asymptotes, you have to think a bit more. The reason is, in order for there to be an oblique asymptote, you see, like if there's an oblique asymptote, there is a function, linear function, such that the difference goes to 0. But this can be anything. How can you check all possible linear functions at the same time? Well, you can't. What you should do is you should try to understand the behavior of your function in the long run, and if there are any oblique asymptotes, they will automatically come out. What do I mean by this? Let's look at this function, x minus 2 arctangent of x. What's happening to the second term when x tends to infinity? It goes to pi, like arctangent of x goes to pi over 2, so 2 times that goes to pi. So the second term goes to pi. The first term is just x. So in the long run, I'm guessing that this is going to look like this function is going to look like x minus pi, which is a linear function. So let me check that. So there are no vertical asymptotes, there are no horizontal asymptotes, but if I check the limit of this function at infinity, not this function, limit of the following, this function minus x plus pi, this limit will be 0 because x's will cancel each other, and this goes to pi over 2, so this limit will be 0. And a limit of the following difference. Now, this time I'm taking a limit at negative infinity. So when x goes to negative infinity, arctangent of x goes to minus pi over 2. So when I multiply by 2, it's gonna this term is gonna go to this term here is gonna go to pi minus pi. So I'm guessing that this limit will be 0, and it is the case because these x's cancel, and this goes to minus pi over 2. Okay. So we have two oblique asymptotes, which are y equals x plus pi and y equals x minus pi. So we have two oblique asymptotes. Now I can sketch the graph of this function. I'm going to sketch it over here. Okay. Oh, I did something. Yes. Okay. So let me read the data of this table. Okay. Between -1 and 1, my function is decreasing. Okay. And between -1 and 0, it's decreasing in a concave down way, then it's increasing in a concave up way. Well, so it looks like this, but maybe it looks like that, maybe it looks like this. So what am I going to do? Like, I don't know which one to draw, so what am I supposed to do? You see, I forgot the third bullet point here. Plug in some sample points. In order to be able to sketch, I need to know where I'm going to start. Like, once I started a point, I know how it's going to curve, but I need to be given a starting point. So let me plug in some sample points. Let's plug in -1. If you plug in -1, you will get -1 plus 2 arctangent -1, which is going to be arctangent -1 is a minus pi over 2, so 2 times minus pi over 4. So this is going to be minus pi over 4, so -1 minus pi over 2. So that's something. Wait, what? I have a minus sign here. Oh, okay. I have a minus sign in the question. I kept writing plus. Clearly, like, this is the reason that I need to have some students warning me real time. Then these will actually flip. This will be minus, this will be plus. I am sorry for this. So I have -1 minus 2 arctangent of -1, and this is going to give you -1 minus 2 times minus pi over 4. So this is going to give you pi over 2 minus 1. So this will be a positive number because pi is like 3.14159265 . So this will be a positive number. So pretend that it's over here. Okay. Now, after this point, it's going to decrease in a concave down way until 0, at which the value of the function is 0. So it's going to decrease like this in a concave down way. Okay, good. What's going to happen after 0? It's going to become a concave up, but it will still be decreasing until 1. And at 1, its value is, you can actually check that it's going to be 1 minus pi over 2. Okay? So picture is going to be symmetrical like this. And at this point, I see a local minimum, okay? And afterwards, it's increasing in a concave upway. Okay, that's fine. It's going to increase in a concave upway. And on left of -1, what's going to happen is, on left of -1, my graph is increasing and it's concave down, so it's going to look like this. Now, we're not done. There are no vertical asymptotes, that's fine. There are no horizontal asymptotes, that's fine as well, but there are two oblique asymptotes. And one of them is y equals x minus pi. Y equals x minus pi looks like this. Okay, so this is going to be minus pi. And I have y equals x plus pi as another asymptote. You see, I have shown here that the limit of this difference, my function minus x minus pi, when x goes to infinity, is 0. So in the long run, it's gonna, like, the graph of this function is going to get closer and closer to this line. And when x goes to negative infinity, the same thing will happen. Okay, so I will have two asymptotes like this. What's the value of this function at that? Okay, this picture is at the moment wrong. I'm gonna fix that. So this is almost correct, except there is one problem. You can ask, like, how did you know that this line is over here? It is actually not. Okay, so I need to move this line down. Okay, so I should take these back. Okay, there are no more undos, so I'm gonna have to erase this by hand. You see, this point is a 1 minus pi over 2, which is like less than, which is greater than -1, okay? So let's say that this is the point, -1. The line y equals x minus pi, when you plug in 1, you get 1 minus pi. So 1 minus pi is going to be, like, when you plug in pi 1, you're going to get 1 minus pi, so it's going to be like -2 point something. So it's going to be over here. So this line actually looks like this. The slope of this line is 1, and similarly this line y equals x plus pi is going to be over here. Okay, so what's going to happen is the graph of this function will get closer and closer to this these lines like this. Okay, okay, so this is roughly the picture. Now let me show you a more accurate picture from Mathematica. Plot x minus 2 arctangent of x, and let's change x between -3 and 3. Okay, so you see this shape which we also got. But I want you to see the asymptotes, so I think I need to do the following. Let me plot two functions at the same time. I also want to plot x minus pi, and x plus pi, and let's say that x is between minus 20 and 20. Okay, yeah, let's make this, let's make x take equal to minus 1, minus 10 and 10. Yeah, this is the picture. Now you can see. The orange line here is y equals x minus pi. This one is y equals x plus pi, and this is my function, okay? And as you can see, that like these lines are the oblique asymptotes of this function, which I also had, okay? I mean, clearly the Mathematica picture is more beautiful, but that's the best I can do. I'm sorry. So this is the graph of the function, okay? Now, let me sketch two more graphs where we're gonna now observe a vertical and horizontal asymptotes, okay? Example. Okay. Let fx be x squared minus 1 divided by x squared minus 4. Now in this question, you see, I'm going to sketch the graph, but in order to sketch the graph, what's the first step? Find f prime, f double prime. Well, this specific lecture is not about differentiation, so I am actually going to give you f prime and f double prime in case I make an arithmetic mistake, in which case it's going to be a disaster. So let me also take a look at the derivative and second derivative of this function. You are given that f prime of x is minus 6x divided by x squared minus 4 squared, and f double prime of x is 6. This is a question from your book. Times 3x squared plus 4 divided by x squared minus 4 cubed. Okay. Sketch the graph of f. Now in this question, I'm given the first and second derivatives as well, because the point is not to be able to find them. The point is to be able to draw, roughly sketch the graph using that, okay? And if you actually look at our past exam questions, which we put online, you'll see that we do this a lot. Like when we want you to sketch the graph function, we don't want you to make any arithmetic mistakes, and we don't want you to lose points just because you made a little arithmetic mistake while computing derivatives. So sometimes you'll see that we'll be giving you these, okay? I mean, when we do exams, when we carry out exams. So what do I want to do? Okay, I'm given the first and second derivative. So I'm going to do this table. Now I have to be careful. What's the domain of this function? The domain of this function is not now all of real numbers. It is all of real numbers except the points which make the denominator 0, which are minus 2 and 2. Okay. So these points are off the table. That's good. Okay. What are my critical points? There's only one critical point, which is 0. I'm not interested in 2 and minus 2, so I'm not going to list them as singular points because they're not even in the domain. So there's only one critical point. And what are the possible candidates for a inflection points? Well, 3x squared is always positive, plus 4 is always positive, so the numerator is always positive, and denominator is never 0 because x is not 2 or minus 2, which means that f double prime is never 0. So this equation gives no real solutions. So there are no points which make the second derivative 0. Okay, so let me fill out my table. No, not triple prime, f. What's the sign of the derivative? Okay, so I have one more point of interest which I should mark here. Is the critical point 0. Okay, what's the sign of the derivative over here? You see, if the denominator in the derivative is always positive, and the numerator is minus 6x. So if x is negative, this is going to be positive. And if x is positive, it's going to be negative. Okay, so my function is increasing here, decreasing here, and decreasing here. Good. What about f double prime? Now, you may think that because there are no points which makes the second derivative of f0, its sign should always be the same. That's not necessarily the case. You see, this denominator will it will actually make a difference. How? If x is less than minus 2, x squared minus 4 is positive. So its cube is positive. So positive divided by positive, it will be positive. Between minus 2 and 2, this denominator is negative because like x squared minus 4 is negative and its cube is negative. And the numerator is positive, so it's going to be negative here. And 4 points bigger than 2 is going to be positive. Okay, so I have that. Good. So this is my table. Now let me check the asymptotes. This function is continuous everywhere except minus 2 and 2, which means that by the previous argument that I told you about in the previous question, at the points which are different than minus 2 and 2, I know that there are no vertical asymptotes. This does not mean that at 2 and minus 2 I have to have vertical asymptotes. I am going to check that. I may or may not have vertical asymptotes at minus 2 and 2 at the moment. So let me check these. Let me check the limit of this function at 2 from right. When x approaches to 2 from right, this top part will be approaching to 3. This part will be approaching to 1. These are positive. And, sorry, this part will be approaching to 4, which is positive. Now, this part will approach to 0, but it will approach to 0 from right with positive values. So, the top approaches to 3, this approaches to 4, and this approaches to 0 from right. So this limit will be positive infinity. Okay. Now this by itself guarantees that there is a vertical asymptote at 2. But I also need to check the left limit because in about like a couple minutes I'm gonna sketch the graph of this. And when x approaches to 2 from left, again, this top will approach to 3, this term will approach to 4, this term will approach to 0, but it will approach to 0 from left with negative values, which means that this limit will be negative infinity, okay? So we have that, and let me check. Well, let me check the limit of this function at minus 2 and minus 2 from left and right. Let's check the limit at minus 2 from right. This will go to 3. Now I have to be careful. This goes to 3, which is positive. This goes to minus 4, which is negative, so I have something approaching to a negative number here. This approaches to 0 from right, because my x is approaching to minus 2 from right, so it's less than minus 2, sorry, it's bigger than minus 2 all the time. When you add plus 2, you're going to get numbers which are positive, which are approaching to 0. So this is approaching to 0. The second term is approaching to 0 from right with positive numbers. So some positive number here, some negative number here, other than 0, and like numbers which are approaching to a positive number here, numbers approaching to a negative number here, numbers approaching to 0 from right here. So if I didn't have this negative part, I would have a positive infinity as this limit, but because of that negative sign, this limit will be negative infinity. And you can guess what's going to happen in the other case, okay? I am directly going to write it down without explaining, because this is like the third time I'm explaining this. So this will be positive infinity. So we have two vertical asymptotes at a x equals 2 and x equals minus 2. Okay, that's good. So we're done with vertical asymptotes. What about horizontal asymptotes? Now, this limit, you can easily check that by dividing top and bottom to x squared. You can check that this is the same thing as like this x squared minus 1 divided by x squared minus 4 is the same thing as 1 minus 1 over x squared divided by 1 minus a 4 over x squared. And when x goes to infinity, this goes to 0, this goes to 0, and this will be 1. Okay? And similarly, the limit of this at negative infinity will be 1. You can check that. So we have the horizontal asymptote y equals 1. Now, the limit of this at positive infinity is 1. The limit of this at negative infinity is 1. So I have horizontal asymptotes, which means that there can't be any oblique asymptotes, okay? Because I already know the limit of this function at positive infinity and negative infinity. They're both 1, so there are no oblique asymptotes. Thus, there are no oblique asymptotes. Okay? Now we're ready to sketch the graph of this function. I'm gonna move this to the left because I realized while watching videos that because you see me on the right bottom corner of the screen, like I sometimes write under that window so you can't see it. So I'm trying to avoid writing on the lower right corner of the screen. Okay. Now I have two asymptotes at -2 and 2, and I have one local maximum by the first derivative test. Local maximum at 0. What's the value of this function at 0? If you plug in, okay, I'm gonna start sketching, so I need to have some sample points. So f of 0 is a 0 minus 1 divided by 0 minus 4, so it's a 1 over 4. Okay, so at 0 I'm over here at 1 over 4, and between 0 and 2 this function is decreasing in a concave down way because it's the second derivative is negative, and over here it's concave up. I forgot to write those. I'm sorry. So because I forgot to write those, I also forgot to say the following. Here's a question. Are 2 and minus 2 inflection points? The concavity changes at minus 2, the concavity changes at 2, the concavity changes at 2 as well, but they are not inflection points because they are not in the domain of the function. Remember, in order for a point to be an inflection point, concavity should change, but also your function has to have a tangent line there. If minus 2 and 2 are not in the domain, there can't be any tangent lines there, so they are not inflection points, okay? Even though the concavity changes at those points, they're not inflection points. Anyway, between 0 and 2, my function is decreasing in a concave down way, and it hits 0 somewhere where if you actually try to solve this equation, you'll get that x is plus or minus 1. So the value of this function at plus 1 and minus 1 is 0, okay? And between 0 and 2, my function is decreasing in a concave down way, okay, like this. And its limit at 2 from left is negative infinity, okay? Its limit at 2 from left is over here. It's negative infinity. So I see this picture. And on left of 0, up to minus 2, like between minus 2 and 0, it's increasing in a concave down way. And its right limit at minus 2 is negative infinity. So I'm going to see a picture which looks like this. Actually, this function is even, so the graph will be symmetrical with respect to x equals 0 anyway, so I knew that. So that's that. Okay, that's good. What happens after 2? It's going to be decreasing in a concave up way. Okay, that's good. And its limit at infinity will be 1. So let me mark a y equals 1. This function, if like on the interval to the infinity, it is decreasing in a concave up way, and its limit is 1. So it has to look like this. And its limit at 2 from right is positive infinity, okay? And when x goes to negative infinity, the limit of this function is 1 again. And on the interval minus infinity to minus 2, it's increasing in a concave up way, so like this. And its left limit at minus 2 is infinity, as you can see over here, which means that it is going to look like this, okay? So this is roughly the graph of my function. Now let me show you a better drawn graph on Mathematica. Okay, so this is like you see the vertical asymptotes here at 2, like this is 2, this is minus 2 at 2, and a minus 2 you see 2 vertical asymptotes, and you see this horizontal asymptote y equals 1, okay? So this is the graph of this function, okay? Now, one final example, and then we're gonna stop. Example is sketch the graph of f of x equals e to the power x times x squared minus 1. Just a second. I think I had another question in mind as well. Do I want to do that? No, I don't want to do that. Okay, that's fine. sketch the graph of this function. Again, let's go back to our algorithm. So the first step is find f prime, f double prime, find intervals of increase and decrease, and concavity. Okay. We have that f prime of x is, I need to apply the product rule, derivative of the first one times second one, plus first one times derivative of the second one. So in e to the power x parentheses, this is going to give me x squared plus 2x minus 1. Okay, so we have that. And let me check, let me find f double prime. I'm going to take the derivative of this final term, derivative of the first one, by product rule. So derivative of the first one, e to the power x times second one, plus first one times derivative of the second one is 2x plus 2. So in e to the power x parentheses, this is going to give me x squared plus 4x plus 1. So if I set the first derivative of f equal to 0, this is going to give me that like e to the power x is never 0, so x squared plus 2x minus 1 is 0. So by the quadratic formula, x is a minus b plus minus b squared minus 4ac divided by 2a. So it's going to be minus 1 plus minus, it is going to be 8. So it's going to be 2 root 2 divided by 2. Okay. So I have minus 1 plus minus 1 root 2. And if I set a second derivative of f equal to 0, I get that x squared plus 4x plus 1 is equal to 0. But the discriminant of this is like b squared. Oh, then that's fine. It has roots. So let's find its roots using the quadratic formula. Minus b plus minus square root b squared minus 4ac divided by 2a. So it's going to be minus 2 plus minus, it's going to be 12. It's going to be 12 here. So root 12 is 2 root 3. I'm dividing by 2, so I have root 3 here. Okay. Now, these numbers are approximately minus 1, minus 2 is approximately, this is like root 2 is 1.41, so it's like a minus 2.41, and this is 0.41, and these numbers are, I'm going to explain why I'm doing this. This is like a root 3 is like 1.7 blah blah, so this is going to be a minus 3.7 blah blah blah, and this is going to be approximately a minus 0.2 something, I guess. The point is, like, I'm gonna draw a table, right? I need to compare these. I need to be able to compare minus 2 plus root 3 and minus 1 plus root 2. I could have actually done this by inequalities. Like if someone asks you which one is bigger, well, this is easy to figure out. Pretend that this is less than that. Put 2 to the other side. Then you need to have that this holds. Okay, and then if you square like this is clearly positive, so I'm going to square both sides, and this is going to give me 3 plus 2 minus 2 root 6. So this holds, and then I'm going to put this to the other side and put 1 over here. this should hold, but is this true? This is not true because this is bigger than a 2. Okay, this is bigger than 2, so this is not true, which means that this is not true, which means that this is not true, which means that this is not true. So this one is bigger. I could have figured these out like that, but I just want to write down the approximate value so that I would see where these numbers are on this table. So here's my table. My domain is minus infinity to infinity. Okay, I think okay, I didn't forget to write these. I thought that I forgot to write these. And this is my domain, and here's my table. I have 4 points of interest. The smallest one is minus 2 minus root 3, which makes the second derivative 0. And I have then minus 1 minus root 2, which makes the first derivative 0. And then I have minus 2 plus root 3, which makes the second derivative 0. And I have a minus 1 plus root 2, which makes the first derivative 0. Okay. So what are the signs of the first derivative and the second derivative? You can actually check that. The sign of the first derivative over here is a negative. Wait, what? No, it's positive, negative, positive. Okay, because I already found the roots of this. This is x minus its first root times x minus its second root. So if x is less than both of these roots, if it's on this interval, then this will be negative, this will be negative, their product is positive. In between these roots, one of these factors will be positive, the other one will be negative, so you'll see negative here. And if x is bigger than both roots, it's going to be positive as well. And the same thing will happen with this one. So it's going to be positive, negative, positive. So my function is increasing concave up, increasing concave down, a decreasing concave down, decreasing concave up, and increasing concave up. So I have a local maximum at minus 1 minus root 2 by the first derivative test, and I have a local minimum at minus 1 plus root 2 by the first derivative test, and I have inflection points. So this is an inflection point at minus 2 minus root 3, and I have another inflection point at minus 2 plus root 3. Okay, so this is my table. Now let me figure out, this function is continuous everywhere, so there are no vertical asymptotes. This time I'm not going to say clearly, there are no vertical asymptotes. There are no vertical asymptotes as f is continuous everywhere. Okay, and the limit of f at infinity is when x goes to infinity, the first term goes to infinity, the second term goes to infinity. So you're taking the limit of numbers which are both tending to positive infinity, so their limit will be positive infinity. Like the limit of their product will be positive infinity. Now, for the limit at negative infinity, I have to be careful. When x goes to negative infinity, this goes to 0, this goes to positive infinity. So I have an indeterminate form of the form 0 times a 0 times a positive infinity. And what do you do when you see an indeterminate form of the form 0 times positive infinity? You flip one of the terms, okay, and you get a something of the form a 0, like you rewrite your a expression using reciprocal of one of the terms. So that will give you 0 over 0 or infinity over infinity, so that you can apply L'Hopital's rule. Remember, we did this earlier. So let me flip the if the first one. Do I want to flip the first one? Yeah, let me flip the first one. So let me rewrite this as 1 over e to the power x. And now, if I plug in minus infinity, this goes to 0. E to the power x goes to 0 from right. So 1 over e to the power x goes to infinity, plus infinity, and this goes to plus infinity. So I can apply L'Hopital's rule, okay? I see infinity over infinity. Let me continue over here. So the derivative of top is this, derivative of bottom is, I'm going to quickly take it, a minus 1 over e to the power x squared times e to the power x. Okay, and then when you cancel these, you will still get infinity over infinity. So I'm going to apply L'Hopital's rule once more. And then this will give you 2 divided by, you see, you get minus 1 over e to the power x. Its derivative is going to be 1 over e to the power x squared times e to the power x. Check that. That should be true. And then this will be a 2 times e to the power x, limit of this thing as x goes to negative infinity, and this is going to be 0. Okay, so we have a horizontal, we have the horizontal asymptote, we have the horizontal asymptote y equals 0. Okay, now are there any oblique asymptotes? I'm going to tell you the answer is no, but I'm not going to prove it. I'm going to explain why there is no oblique asymptote, but I'm not going to give you the proof, because the actual complete mathematical proof of that would be unnecessary for this course and a bit difficult for you. You see, this is going to infinity, but when x goes to infinity, but this going to infinity does not prevent this function from having an oblique asymptote, because a linear function goes to infinity. But what happens is this is actually this is growing too fast to have an oblique asymptote. Okay, I actually lied. It's not that difficult. But the thing is, take any linear function, subtract that from this, and show that no matter what m and n are, this limit is actually positive infinity. This grows way faster than any linear function. Okay, this is not difficult to show. I thought it would be difficult, but for this example, it's not. You can actually show that this is always infinity, so there are no oblique asymptotes. Okay, but in general, it may be difficult to show that there are no oblique asymptotes, because you have to actually figure out how fast your function grows in the long run. And even though for this function it's easy, in general, this may be difficult. Okay, but let me write that as well. For any mn, the limit of this difference will be infinity, because x is going to infinity. For x for positive x, this will be bigger than or equal to 1, so this will be x squared minus 1. This is a second degree polynomial. It will go way faster than a first degree polynomial. You can simply you can also observe this as follows. If x is bigger than m plus n, this term, where the difference between these terms, well, okay. I mean, we already proved that this difference is like if x is positive, this is bigger than 1, so this difference is bigger than x squared minus mx minus n minus 1. So this is this difference. What we proved that the limit of such a polynomial at infinity is infinity, so this limit is infinity. So for this example, it's not actually difficult to show that there's no oblique asymptote. So this is always infinity, so there are no oblique asymptotes. There are no oblique asymptotes. What I meant to say was that in general, it may be difficult for you to actually prove that there are no oblique asymptotes because you have to show that your function minus a linear function doesn't have a limit 0 at infinity, but checking that limit depending on what kind of function you have may be difficult, okay? Well, for this one, it's not. So there are no oblique asymptotes. So let's sketch the graph of this. I have 4 points of interest. Minus 2 minus 3 e minus root 3 minus 1 minus root 2 minus 2 plus root 3 and minus 1 plus root 2. Okay, now I need to plug in these values and see what I get. Oh, it's going to be terrible anyway. What's the value? The value of this function at minus 2 minus root 3 is going to be a positive, okay? So the value of this function at minus 2 minus root 3, it's going to be positive, so it's going to start somewhere over here. And up to this point, a minus 1 minus root 2, it is going to increase in a concave down way. So it's going to increase in a concave down way. And at this point, I see a local max at minus 1 minus root 2. And afterwards, it's going to decrease in a concave down way up to minus 2 plus root 3. Okay? And you can check that the value of the function at minus 2 plus root 3 is going to be negative because this number is less than minus 1. Sorry, it's bigger, it's between minus 1 and 0. Okay, this is between minus 1 and 0, which means that if you take its square, it's going to be less than 1. So when you subtract 1, it's going to be negative. So something like this happens. And then at this point, let me draw this again. It's increasing concave down, it's increasing concave down. And at this point, there's it's an inflection point. The graph changes its concavity. It starts to curve up. Well, I shouldn't say up, but it starts to curve kind of upwards, okay? It's going to become concave up. And it's still decreasing until minus 1 plus root 2. So it is going to still decrease up to this point. And afterwards, it's going to increase, and its limit at infinity is infinity, so it's going to go like this. And what's going to happen on left of a minus 2 minus root 3? You see, this is also an inflection point. On left of this, my function is increasing, but in a concave up way. And its limit at negative infinity is 0. So when I go to negative infinity, this should go to 0. And my function is increasing in a concave up way. So this is roughly the picture. Okay? So this is y equals f of x. And let me show you the actual picture from Mathematica. I shouldn't really say actual picture, but the graph, which is better than mine. a graph which is better than mine, e to the power x times x squared minus 1. Okay, this is not doing what I wanted to do. It's still, these are too big, so 2 here. I want you to see that those points. Yes, good. Now, when I plot this between -3 and 2, you see this picture. Let's go up to -4 actually. You see this picture. Now, what's the value of this? This is like minus. This is something like minus a 3.7 blah blah. As you can see, over here, somewhere over here, I have an inflection point. On this left part, it's concave up. Somewhere over here, it changes its concavity. It becomes concave down. And at this point, which is a -1 minus √2, it's like minus 2 point something. There's a local max, and afterwards it starts decreasing in a concave down way. And over here, somewhere over here, which the exact point is -2 plus √3, it becomes concave up. It still decreases, and there's a local min here at the point -1 plus √2, and afterwards it's increasing in a concave up way. Okay, and this is the graph of this function. Okay, so we've seen 3 examples. In this example, we have 1 horizontal asymptote, no vertical asymptotes, no oblique asymptotes. In the previous one, we have 2 vertical asymptotes, 1 horizontal asymptote, no oblique asymptotes. And in the first one, I have no vertical asymptotes, no horizontal asymptotes, 2 oblique asymptotes. So we've seen 3 examples, and in your recitation, you're going to solve more questions of this form, like sketch the graph of blah blah. What are our steps? Let's go over this and finish the lecture. Find f prime, find f double prime, and then find the intervals of increase and decrease, find the concavity of f using a table and using the first and second derivative tests. Okay, I mean, you realize that I didn't use the second derivative test at all today because the first derivative test was sufficient, but if you want, you can use the second derivative test as well, but that's kind of unnecessary because once you figure out the science, the first derivative test tells you everything. And after you find these, you check for the asymptotes. There are 3 kinds of asymptotes: vertical ones, horizontal ones, oblique ones. So you check for these by checking the limits at infinities and by checking whether there are points at which right or left limits may be plus or minus infinity. And then this, to supplement this data, you plug in some sample points. Maybe you plug in these points of interest, these inflection points, local maximums, local minimums, to see where you should start drawing your graph off. Okay, so you do this, and when you combine this data, you will roughly get the graph of your function. Okay, so that's it for today's lecture. Stay safe.